Yeah, thank you. First of all, I must thank the organizers along with the ICTS. It's been a wonderfully conceived and organized meeting. It's been a pleasure to uh, talk here. So, we will discuss pseudoscalars from dark extra dimensions and their possible relevance to the dark matter problem. And we will also try to see to what extent the physics of these pseudoscalars is similar or different to the axion-like particles, which define the more standard paradigm in addressing the dark matter problem. So, to put things into perspective, let us make a few general remarks first. In physics, there has been a few remarkable instances where an idea itself has gone further than the original purpose behind its very inception. And perhaps the idea of extra dimensions is one such example. Now, one of the earliest applications was due to Kaluza in his bold attempt to unify Einstein gravity and Maxwell theory in one higher dimension. And Klein essentially proposed a justification as to why we won't practically see this extra dimension. Okay. So this is a cartoon of the Kaluza-Klein idea, where this is the compactified fifth dimension and so on. Now there has been other scenarios also based on large or warped extra dimensions, but this is not a talk about extra dimensions, so I'm not going to delve on those things. Of course, basically all of these are essentially based on the Kaluza-Klein formulation. However, in general, any such formulation predicts an infinite tower of massive excitations, which are expected to be seen at the colliders at some energy, and these are supposed to be the proof of extra dimensions. However, there has been no trace of this massive excitations till now. So, of course, that means that we can keep on exploring alternative ideas on extra dimension, and here we will precisely do that, but with the motive being trying to apply it to the context of the dark matter problem. In other words, here we discuss a new formulation of extra dimension based on the idea of a fifth dimension of vanishing proper length in the framework of vacuum gravity, so no matter coupling. And we will also show why such a framework could be relevant to the dark matter physics. Further, it exhibits a pseudoscalar structure. Of course, in general, it can be termed axion-like, but I would prefer not to use that term because we will see that the physics is quite different. And we will also discuss the potential implications. Now, in passing, it's worthwhile to emphasize that this extra-dimensional formulation, as it is has some economy in the sense that the fifth dimension is not detectable in principle because its proper length is 0. And also one doesn't have to then worry about whether it should be small or large or warped, and then the associated phenomenology of the Kaluza-Klein towers, for instance. Okay. So let us now spell out our basic formalism that we propose a five-dimensional action in the first order framework in vacuum, where we have 5 coordinates, t, x, y, z, and v. So v is our fifth dimension, if you like. And then this is the, of course, the standard vacuum action, just that in 5 dimension written in terms of first order variables, tetrads, and the connections. Tetrads are the e's hatted, and connections are the omega hatted. Hatted means they are 5-dimensional objects. And some of you may be more familiar with the wedge notation, so both are here. And when you vary with respect to the basic fields, which are these are pentards now. So the pentards and the connections, when you take a variation with respect to them, you get two sets of equations of motion. And we want to analyze the solutions of these equations of motion. Now, to explore the consequences of an extra dimension of zero metrical length, we need to find the most general solution where the pentard has a zero eigenvalue. Okay, that means the pentard is degenerate. Now, the zero may be chosen to lie along the fifth direction, and it can be put in a simpler form like this by using the SO4,1 rotations on a general pentard with a zero eigenvalue. And note that since it has a zero eigenvalue, it has no determinant, the pentard, but this emergent tetrad here does have inverses, okay, and it can still define a four geometry. So it defines a smaller four space-time. Now, I don't have the time to go to the details of how the equations of motion could be solved and all, but I will just mention the essential result which comes out. So when one writes down the emergent theory coming out of the most general solution of these 5D equations of motion, what one finds is that there is an emergent theory in the fourth dimension where this is the four-dimensional Einstein tensor written in terms of this metric defined in terms of this four-dimensional tetrad here. And then there is an emergent energy momentum tensor, which however is purely geometric. Okay. And each of these pieces have their own meaning. Now, the last three pieces, which I call L square, A square, and chi square, they essentially originate due to non-vanishing torsion in the 5 geometry, which is defined by the non-invertible pentad. Okay. And note that I have defined these objects here. These are essentially quadratic fields, but they have no derivatives. So what it means is that these fields appear only in algebraic combinations, but not through space-time derivatives. So they are not dynamical or not propagating. And they only have gravitational interactions because they cannot couple to matter in 5D because the 5D metric is degenerate. It doesn't allow matter coupling. Now, each of these pieces can be analyzed in terms of a perfect fluid model, and then what one finds is that this traceless tensor, that's quite obvious, it acts like a radiation. And this, after some analysis, it turns out to have an equation of state of -1/3, which is negative pressure. This has a stiff equation, which is +1, and then this acts like a cosmological constant. Of course, this is a constant here, but in general, you can have this as a field. However, we don't consider that case. We are going to consider the case where this acts like a cosmological constant. So it has an equation of state -1. And if we demand that the individual energy densities are non-negative, then the equation of state of this whole fluid is bounded, and the bound is just this. Okay. Now let us interpret this field content. Of course, this piece is like a cosmological constant, but then this means that this also sets the length scale of the multiplet because the length scale of this multiplet has a common origin in the 5D connection. And this length scale, because it's the emergent cosmological constant, is large and it acts over distance of the Hubble scale. Okay. So that's the first thing to note. Secondly, as an effective energy momentum tensor, it is straightforward to see that this effective density here, that actually goes like 1/g L square, where L is the length scale of these fields. And that means it goes as m Planck divided by L Planck into L square. And this is unlike ordinary matter scaling, where the density is typically scaled like mass, where mass is the mass scale associated with a field. and then length q. So in other words, these densities, they have no inherent mass scale of their own. Okay. So this also means that they are non-particulate. They can't be identified as particles naively. And that also means that these fields cannot exchange energy through collisions with matter particles. In other words, they're inert in that sense. However, one can still invoke some effective matter coupling in these 4 dimensions, which we have not done here. But then one finds that such couplings with these fields, L, S, etc., they have to be Planck suppressed. So even in that sense, they are non-interacting. Okay. Now, in view of this strongly suggestive features, what we propose is that the non-propagating geometric field multiplet, which is a radiation L and S. L is an axial vector, S is a symmetric tensor. So that should supersede, or that could rather supersede the notion of dark matter. And remember, we are talking about a vacuum gravity theory with an extra dimension of vanishing proper length. So this is our main proposal here. Now, even if this theoretical framework looks provocative enough, it must face up to the challenge as to how much of the observational data it could explain, right? And this, of course, needs a long and elaborate effort. And I'm not claiming that all that has been done. There's a long way ahead. Now, point is, does it suggest anything beyond the standard scenarios in the context of the dark matter problem? So we are slowly coming to that. But before that, let us note the pseudo-scalar structure, which is hidden within this theory. Of course, this content L square, which is quadratic in the axial vector LA, that underlies a unique pseudo-scalar mode phi. Okay, and that when you break it up, that actually through this term contributes to the effective energy momentum tensor like this. It's a simple decomposition. And now this is a pseudo-scalar which emerges here. But point is, this pseudo-scalar is not the other pseudo-scalar, which is a standard axion, which we are familiar with. Firstly, because of the sign. The axion kinetic term gives a minus sign here, but here we have a plus sign. Also, there is a Planck suppression, so that means these are naturally weakly coupled, and one doesn't need any extra physics because of that. And of course, we have not added any potential as such corresponding to these phi terms. Okay, so this is at the very basic level where this is coming out of a 5D vacuum theory. And these are the consequences in terms of the axion-like structure. And of course, this also has a different equation of state, because if you remember Vivian's talk or some of the other talks, you will see that when you add the axion potential to the kinetic term, the equation of state has a range -1 to 1. But here, of course, this phi also has the equation of state strictly -1/3, which is due to the fact that this essentially comes from this axial vector. Okay. So its physics is bound to be very different. But point is it relevant in the dark matter context? So now with these essential structures in place, let us now apply our generic framework with the pseudo-scalar structure as mentioned directly to the case of rotation curves in spiral galaxies, because that has been one of the main motivations behind the dark matter hypothesis. So now just some basic remarks that what does one mean by rotation curves? While Newtonian gravity predicts a falling velocity profile at the outer regions for test particles for spiral galaxies, observations confirm otherwise. It says that rather has a flat profile and not, it doesn't fall off. And that started with the observations of Rubin and Ford and so on in the particular context of rotation curves. even though the word dark matter has been invoked earlier and the necessity of it has been felt earlier by people like Zwicky and others. Okay. So this is Vera Rubin and this is Ford, of course, with their instrument with which they're doing such observations. And of course, you have seen better rotation curve profiles. So let me not, you don't have to look at this for a long time. But these are the rotation curves with a flat profile, okay, taken from some paper. Now, in this context, what are the basic questions to be chased? Of course, one can ask, could the flat rotation curves, by the way, I hope somebody is not trying to ask a question. I just heard some noise.
No, it seems you can go. It's no problem.
Oh, okay, all right. So the relevant questions here, of course, the very basic questions are that could the flat rotation curves emerge as dynamical solutions of the equations of motion elucidated here? Also, is there a natural explanation of the stability of the galactic halo? Then is there a way to predict the constitution of the halo fluid and also its equation of state? And finally, is there any possible imprint of the emergent pseudo-scalar structure just talked about? Okay. So let us see if we can answer some of these. Now, how we are just going to adopt the standard way of modeling a halo in a spherically symmetric general relativity case. So we assume a spherical symmetric static metric of this form where there are essentially two functions which just depends on the radial coordinate r, which have been determined through the equations of motion, and the circular velocity for test particles at some particular radius r is given in terms of this metric function mu of r. You can just insert this metric into the equations of motion which we had seen earlier, and it turns out, of course, we can't show that it is here, but it turns out that the resulting set of equations indeed admit solutions which exhibit flat rotation curves. Now, in the subsequent discussion, we will just ignore the radiation piece in this dark emergent multiplet for the sake of simplicity. Now, how do the solutions look like? In fact, these are very well-known solutions. So let's think of the Newtonian limit of very negligible pressure, where you get these solutions for the metric functions essentially. Okay, so there is a non-trivial radial dependence for the first function, but the second function is a constant. And this essentially corresponds to the equation of state of the halo fluid where it's close to zero. Now, in our picture, this is corresponds to the scenario where the axial vector dominates over the second rank tensor field. Okay, and the ratio is precisely this. However, there is also a non-Newtonian solution for the flat rotation curves, and that looks like this. The first metric function is the same as earlier, but then the second metric function is not a constant anymore. It has a non-trivial radial dependence. And this also has been talked about in earlier literature. And interestingly, this corresponds to an equation of state of -1/3. And this is not really talked about so frequently in the literature, by the way, but people have found it, in fact. That's what I noticed. And in our framework, this corresponds to the picture where the axial vector is dominant. And the tensorial contribution to the total halo fluid density is very small. Okay. Now, what is the most general solution? Of course, where you have both these scenarios, and then the density looks like, which has a 1/r² fall off. That's the standard behavior you want. And then there is this non-Newtonian part. Okay. Interesting thing is this, as I already said, this corresponds to the non-Newtonian part corresponds to an equation of state of -1/3, as is obvious. Okay, and the first part corresponds to zero equation of state. Now, point is, the question one can ask is, I think that is quite relevant, is that is there an explanation of this non-Newtonian behavior at all? And for that, just recall that our pseudo-scalar, which we talked about, that has the same equation of state, which is -1/3. Okay. And also note that this phase of this negative equation of state in the rotation curve, that cannot be explained using a dust-only dark matter hypothesis. Now, one can, of course, ask that why is this not talked about in usual rotation curve discussions? Perhaps because this behavior has a very, very slow variation compared to this, and our observations are not precise enough to notice such a term. I am not an expert on this, but theoretically, at least, you should expect such a behavior. Point is, what is the strength? And this is highly suppressed due to Hubble scale dependence here, which I have not put here explicitly. Okay. So this you can take as an imprint of the axion-like structure, which we had talked about earlier. However, it's not an axion, as I have also emphasized. Now, what is the other new physics, which is interesting in this context? Of course, the other physics is we have already said that the scale of the non-luminous field multiplet, which emerges here in this context, is filled by the emergent lambda, or cosmological constant, in this description, right? And that has this value 10 to the 26 meters. Now, in our framework, there is no other length scale from the 5D theory, so this is the only scale which should generate any typical length scale of the galactic physics, right? Now, it turns out that is indeed the case, because empirically, we already know that such a scale is defined by the typical galactic accelerations, and that is essentially the this is the standard notation for such an acceleration scale in galaxies, and that is this, and in units of c equal to 1, that is precisely this, inverse of this rather. Okay. So thus, in our theory, all the scales is that the length scale of the field multiplet, and the dark energy scale, in the sense that it defines a cosmological constant in the emergent theory, and the galactic length scale, all these are tied up, and they all have a common origin, and the origin is just the length scale of the 5-dimensional connection. Okay, and by the way, this may be contrasted with other standard paradigms like MOND, for instance, which assumes the existence of a new fundamental length scale A0, whose origin has, by the way, no explanation with those frameworks as they are. So now it's time to summarize that what we have gained from this exercise. Firstly, we have explored the dynamical implications of a gravity theory with an extra dimension of vanishing proper length in the context of the dark matter problem. We have seen that the emergent 4-dimensional theory exhibits a field composite which is proposed to supersede the dark matter. And what are the main imports we have talked about? Of course, this provides a dynamical and purely geometric basis to understand the stability of the halo, the constituents of the halo, which are well defined here, its equation of state, which has a precise bound, and also how rotation curves could arise as dynamical solutions of equations of motion. And why I say that it explains the stability of halo naturally, that's because of the inherent inertness of the field multiplet, because of various features we had explained in some detail earlier. And it can also predict something, and namely, it can predict the relative contribution of these various constituents of the halo, which are these fields, if the total equation of state is given of the halo fluid, right? So it can predict something. However, let me not go into these numbers here. Now, of course, one should admit that at this stage, honestly, it would be premature to assert that one could indeed obtain new testable constraints. However, along with cosmological observations, such a possibility seems to be very much open. And there are many things to explore which has not been discussed here, because this has been the first discussion, or just a basic layout of the original framework. But then, of course, one has to explore further things and further details, which involves the full cosmic history based on this theory, and then whether it has any implications for the CMB physics. Of course, it has. And what does it mean for the non-spiral galaxies? And then how does this picture relate to the baryons when matter coupling is brought in the four-dimensional effective theory? So some of these are in progress, but then, as I said, there is much to be done. So with this basic message, I would like to end this talk, and I must thank you for your attention.
Thank you for the talk. So there is one question by Shriyari. Are these solutions stable against small perturbations? So perturbation stability.
Yeah, so the perturbation theory has to be done. As I said, this has not been done. So a full perturbation analysis has to be done.
Mm-hmm. That would be nice, yeah.
Yes.
I have a question. Of course, this goes beyond. Do you have any idea how difficult it would be to really have a dynamical simulation of such dark matter? Would that be just very difficult, or?
You mean you mean numerical simulations?
Evolutionary, the evolution of such dark matter, yeah. Very difficult.
Oh, you mean, okay. Theoretically, you mean the cosmological evolution, perhaps?
Yes, yes.
Okay. Yeah. That is not too difficult, in fact, and part of it has been done.
Oh.
So all you have to look at is how these new multiplates behave, the LS and this dark radiation, because that is not the usual radiation which we have. And then, of course, you can bring in additional effective 4D matter also. So there would be various phases of domination by various field contents, and then the full history will depend on that. But roughly what I can tell you is that this predicts an early phase of a stiff field domination, because there is an equation of state W equal to 1. Okay, and then that also predicts a late phase, which is new, which is dominated by this axial field, which has an equation of state minus 1/3.
Mm-hmm.
Okay, so the matter density should fall off like 1/a square, and that should have some important implications for the late time cosmology.
Yes, thank you. We can take one more question here on the chat, and this is from Patrick Dasgupta. As L and S fields appear as algebraic combination in the right-hand side of the effective Einstein equation, how would change in the geometry dynamically change the L and S fields? Do you understand the question?
How do you change the geometry dynamically? Our basic dynamical theory is a 5-dimensional vacuum action, right? The first order action. And probably you have to introduce certain terms which you mean, but then the physics depends on that, what you are going to do. However, since the pentad or the 5 metric is degenerate, you don't have much choice there. You have to be very careful about what you are going to couple to this theory. For example, 5D matter cannot be coupled in the 5D theory because 5 metric is degenerate. You can only couple matter in 4-dimensional theory. In fact, that is a nice feature that says that this fields can't really talk to the 5-dimensional matter, and no such matter coupling can be induced in the 5D theory, and these have to be non-interacting. And some of these properties are very difficult to get in the standard dark matter paradigms.
Okay, thank you. This is, of course, always a disadvantage of an internet conference that it's not clear. I just got an okay from Patrick Dasgupta that you have addressed this question, I guess. So the organizers, thank you once more for the talk. The organizers would like to stay on for a moment because they have to make an announcement about one of tomorrow's talks.
Yeah, thank you. Thank you.